Okay, so my name is Paul Suhler. I work for Kioxia as a standards engineer. I'm also the chair of the IEEE Security and Storage Working Group. What I want to talk about today are some relatively new developments in different security algorithms. Here's the abstract. You could read that on the website. So the stuff I'm going to talk about are, to go through it, and this isn't real well organized. Some of the existing encryption algorithms suffer from different weaknesses. There are symmetric encryption algorithms. Some of those are weakened as sizes of devices increase, and I'll go into the details of that. One algorithm has been broken, and we had to rip it out. And some other existing algorithms are somewhat weakened by quantum computers. Those are symmetric encryption algorithms, which are the ones used to encrypt the mass of user data that goes into a storage device. On the other hand, there are asymmetric encryption algorithms, which are, they're the basis of public key infrastructure. And everything we've had until very recently have been broken or potentially will be broken by quantum computers. I'm also going to talk about transitions to post-quantum cryptography, the different algorithms I'll talk about and where the requirements are and what the timelines are for that transition. So I assume everybody knows this, but I'll say it anyway. A symmetric encryption algorithm is one where the same key is used for encryption and decryption. The one everybody knows is the advanced encryption standard, which began life 20 or 25 years ago as RINGEL. If I'm saying that correctly, it was a submission to a NIST competition to come up with a standard encryption algorithm. Those are efficient for encrypting and decrypting large amounts of data. On the other hand, there are asymmetric algorithms where you use a different key for encryption and decryption, or I should say different keys. The way those are used for public key infrastructure is that anybody can take a public key for a particular entity and use that to encrypt a message to that entity. But only the holder of the private key, which is always kept secret, or better be kept secret, can decrypt that message. Similarly, you can use a private key to encrypt an outgoing message. Anybody can decrypt that with the public key, and they'll know that it really did come from the holder of that private key, unless, of course, there's been a security breach. Problem is, those are inefficient if you're going to do if you want to encrypt large amounts of data. So you'll typically see things like use a symmetric algorithm to encrypt a lot of data, and then the key for that is encrypted using a asymmetric algorithm, or even the symmetric key and some identifying data is encrypted with another symmetric algorithm, and the key for that is encrypted with the private key. Okay, symmetric keys though, they are relatively small, and they can be, like, as I was just saying, say it in other words, they can be transmitted when they are wrapped with an asymmetric algorithm. Or like I said, there may be two layers of wrapping. So what are the standards? The AES, Advanced Encryption Standard, is NIST FIPS, Federal Information Processing Standard 197. To avoid confusion, everybody talks about FIPS certification. That's specifically FIPS 140-3. There are many other FIPS standards besides that one. Now that goes back to, I think, about 2001. It had some kind of editorial updates in 2023, so that's why I'm saying the latest version of that. But it's been around for a long time. The next one I'll be talking about came out of IEEE years ago for encryption for storage devices like self-encrypting drives, and that algorithm is called XTS-AES, and I'll expand that for you. It's an ugly multi-level acronym, but that's standard 1619, and we just came up with a new version of it that's been published this year. Finally, there is another one for so-called wide block encryption. That's IEEE 1619.2, and we were just notified about a week ago that that's approved for publication, but it's not out yet. And I'll talk about the problems with the algorithm we had to take out. Okay, 197. advanced encryption standard. And you're going to see me hopping in and out of post-quantum cryptography. I've got a whole section on that toward the end, but I have to mention it up here. So the current version of 197 has 3 key lengths, 128, 192, and 256-bit keys. For post-quantum cryptography, only 256-bit keys are going to be allowed. The 128 and 192-bit key lengths are being deprecated. And I'll talk a little more about that later. Interestingly, NIST has now begun work on a newer, wider form of that algorithm. The original AES encrypted things in blocks of 128 bits at a time. The newer one is going to go to 256 bits, and it will only use 256-bit keys. So there is an initial preliminary draft, and when you get this presentation, you can follow that and look at what they put out for comments. And I think you can also see the comments they got back. The initial comment period has closed. But this is a work in progress. It's not required by some of the stuff I'll be showing you later. Any questions so far? I have enough over what will probably end up being empty time in my talk that if you want to ask questions as we go along, that's fine. Okay. So 1619. The title of this was Cryptographic Protection of Data on Block-Oriented Storage Devices. It defines the XTS-AES mode, which is XEX, tweakable block cipher with ciphertext stealing, and XES expands to XOR encrypt XOR, which gives you a little bit of insight into the process of how that cipher works. And I guess I have to give you a caveat. I am not a cryptographer, and I do not even attempt to play one on Zoom, so I can't go into the details of a lot of these algorithms. Anyway, so what this is used for is a lot of self-encrypting hard drives and SSDs. In fact, I'm not sure if there are any other algorithms that are used by self-encrypting drives. An important keyscope or an important concept is what's called keyscope. That is the number of bytes that are encrypted with a key, a single 192 or, 128, 192, 256 byte key, whatever was done in the device. So until very recently, and I don't know if this is changing fast enough, typical implementations would encrypt all the data on a device with a single key. If you want to sanitize it, you blow away that key and all the user data is no longer accessible. Now, that works okay for smaller devices. But as device capacities are getting very large, and my company announced one at FMS with, I think, 247 terabytes, and they're going to continue to increase. And if you look at using this encryption algorithm for encrypting data that spans multiple devices, the devices are getting bigger, hundreds of terabytes, excuse me. And the data sets from large systems that span multiple devices are getting up into the exabytes. Well, we were contacted by NIST, and they pointed out that as these things get larger, that gives someone attempting to brute force an attack on figuring out the key, that gives them more and more data to work with. For example, if the keyscope, the amount of data encrypted with one key, is a petabyte, which is only about 4 times the largest announced SSDs, there is a 2 to the minus 37 chance of succeeding in any given attempt at the brute force attack. That's about 8 in a trillion. Now, for some people, think nation-state security agencies like our NSA, that's an unacceptable risk. If the data gets even bigger, up to an exabyte, then you end up with a chance of 2 to the minus 17, 8 in a million, and that's really untenable for many users of this algorithm. And I have to point out, this does not require a quantum computer running what's known as Grover's algorithm. This is with current technologies. So what do? What we did in this year's version of 1619 is to limit the key scope. And what that means is you may have to use multiple, what we call media encryption keys within a single device. And that complicates the devices. So here are the new key scope limits that are in this new standard. Yes? Yes. That means brute force attack is where you just try different keys. Each time you try a key and see if you can decrypt the data, that is one of these, one try. And so for a petabyte of data, you have about 8 chances in a trillion of getting it right on any particular trial. Then you would try a different key, try decrypting again. Now, yeah, there are all sorts of things around that, and I'm not a cryptologist. How do you know you've actually encrypted the data correctly? Well, you're generally going to have some idea of what it looked like. Back in World War II, the people at Bletchley Park decrypting German transmissions, they knew pretty much what the format of the messages were, and they could recognize German words. So that you can, if you get it right, then you'll see things you can recognize, and tells you if that trial actually came up with something. But that's a whole other area of cryptology that I am not an expert in. But yeah, so each trial with a different key has these possibilities of success. Did that explanation make sense? Okay. So here are the new key scope limits that we have put in. We have a should not exceed limit and a shall not exceed limit. You should not encrypt more than 1 terabyte, 1 TB of data, which is 2 to the 36 AES encryption blocks with 1 key. And you shall not encrypt more than 256 TB bytes, 2 to the 44th encryption blocks using a single key. So obviously, we have devices that if they're going to follow the tighter limit of 1 TB byte, they already need to be handling multiple keys. And I'll point out that there are devices that can handle multiple keys. TCG Opal devices that implement configurable namespace locking have facilities for a different key per namespace or even a different key for a range of logical blocks in a namespace. So some people have the rudiments of support for that, but a lot of people don't. Okay. Another thing you have to realize is that the key scope, yeah, Bill.
Yeah. One of the mechanisms that you can deal with would be like with any kind of login where after a certain number of brute force attacks, you just close the hole.
There are.
Is that deprecated because that could cause a denial of service attack?
Not denial of service, but there, yeah. Yeah, John? Oh, I'm sorry, yeah. Hey, hang on. Let's make sure that's on.
Shall I repeat the question?
Yes,
okay.
please.
So repeating the question, the question is one of the ways that we deal with that with logins is blocking after 3 failed attempts. Yep. In theory, that would discourage a brute force attack. But I'm just wondering if that approach is deprecated in this sense because that could cause denial of service types of attacks to be successful in shutting down a pipeline.
That's all true, and there are, I know some NIST at least one NIST standard that addresses the number of tries you can make over the interface. But this assumes that you can take the device apart, we call it an advanced laboratory attack, read all the data off into your supercomputer and hack away at it. So what we're trying to do is make sure even attacks like that will fail, not only attacks over the interface. Yeah, those are a lot easier to defend against, as you say. You rate limit the number of queries, or you lock it up after 1,000 failed attempts or something like that. Okay, but
sorry.
John?
A quick one. I believe an AES encryption block, what you're talking about there, are the 128 byte blocks, not
128-bit blocks, so 16-byte blocks. Yes, that's absolutely true. This has nothing to do with a logical block size, which could be 512, 4K, or who knows what. This is AES. Yeah, thanks for clarifying that. Okay, so
I guess.
yes, Shyam.
So does this kind of key scope limits mean that you're going to see devices with like namespaces that don't exceed those sizes and those kind of, that's the intended consequence of this?
Those are implementation details that this standard does not address. How you do this is, up to the device manufacturer. I would think it would probably be too limiting to say never have a namespace bigger than that. But that's way outside the scope of this IEEE standard. But yeah, what? Say again?
If you write the same byte.
Oh.
Doesn't the standard also cover the time concept that if you write the same byte that many times, that you're supposed to then change the key because you've now exceeded that limit?
It depends on, again, how, yes, that's a chosen plain text attack. But the main thing is how many bytes are encrypted with, that makes it a lot easier if you can control what's written on the device. A lot of the attacks depend upon what's called harvest now, decrypt later, which is why stuff that's been on disks for years may be at risk in the future. But okay, let me move on right now. Important thing is that the keyscope includes all the data on the device. It's encrypted with a single key. And it's not only the data readable through the interface, but also data in deallocated blocks. Deallocated blocks can't be accessed through the interface, but they're there, and if you take the device apart and use a low-level attack to pull it all out, then you can use that. So the keyscope has to include even deallocated data. This is starting to turn into a management problem that has to be dealt with inside the device firmware and maybe hardware. Okay, it requires the devices to manage multiple keys. So when you get a read request in, you've got to go find the proper key for that logical block. And that's some new overhead that we generally have not had to deal with. And the same thing, because this algorithm can be implemented by host-based systems that are doing encryption, say, in the CPU, all these limits apply to that as well. It's not only SSDs and hard drives. Okay, there was another standard done, I think the most recent iteration was from 4 years ago, called 1619.2, was wide block encryption for shared storage media. I am not sure how many devices actually implement this, but when we went out and searched, we found that there were references to it, so it's possible it's actually used. It does bigger blocks than 128-bit AES blocks. They're pulled together. Now that defined two modes to be used with AES. One was called encryption with associated data, EME2-AES, and then another one called extended codebook, XCB AES. In late 2024, there were two papers, I think one from Belgium, one from China, that were published, and they show how XCB by itself can be broken. So one of the guys from China came into Security and Storage Working Group, and we looked at this and we said, well, there are references to EME2, but we definitely need to get rid of XCB AES. So it's kind of a cleaving that out. And like I said, we just heard last week that this has been approved by IEEE for publication, so it should show up by the end of the year. I don't want to say that that process is as efficient as it ought to be. Anyway, so that will be coming out. Again, I don't know if any of you actually use that, but just be aware. So I guess most of what I'm going to talk about, and let me see how I'm doing on time, is about post-quantum cryptography. I want to talk about the threat that quantum relevant computers present to us, talk about some of the algorithms that can be used to fight back, talk about hybrid algorithms, which Jeff Hilland mentioned in the previous talk, and then the effects on some of the protocols. I'm not going to try to go into depth on any of these. I just want to give you an idea of where the minefields are. So the quantum computer threat. There are quantum algorithms that exist today that have existed for decades that will break, well, it's Peter Shor's algorithm that he came up with over 30 years ago. They will break classical asymmetric encryption. I can say a little bit more about that. So when cryptographically relevant quantum computers, that's a term NIST came up with, when those are available, they'll be able to attack data that has been encrypted with classical algorithms. Remember, it's not just the mass of user data that's encrypted, but if somebody has harvested your transmission of keys, of establishment of shared keys in the key establishment protocols, they'll have grabbed that too. And they can attack those with these algorithms, with Shor's algorithm. And then they can unwrap the key and they can get the user data, even though they haven't broken AES per se. They've been able to get the key. Okay, so
this is a concern for captured conversations also.
it's a concern for stolen devices, for captured conversations, data that's shipped between hosts and storage systems. Yeah, everywhere. Yeah, it's a big problem. So some algorithms, and I'm going to enumerate those. They've been developed to protect against attacks by quantum computers. And what I was just saying is that the next bullet, which is you can harvest now and attack later when a quantum computer is available. And there is an interesting concept called Q-Day. And it's not when a quantum computer is able to crack your data, it's when you found out there was a quantum computer that can crack your data. And there may be a long time between one and the other. Anyway, so as I said at the beginning, asymmetric algorithms like RSA, those are the ones that are most at risk. Symmetric algorithms like AES, not so much. So what?
This is all web traffic right now.
A lot of, yes, because RSA,
Public web.
yes,
That uses certificates.
that's right. RSA and Diffie-Hellman are, those are at the heart of TLS, cipher suites. And yeah, so all of that is at risk. Now, I don't know enough to go into the details, but Shor's algorithm does three things. It solves the problem of factoring large numbers that are products of two large prime numbers. It solves a discrete logarithm problem and period finding. And those last two attack different versions of Diffie-Hellman. And honestly, I don't understand those well enough to explain them even at the high level I explained factoring. Let's see. Trying to think, I thought I had another idea in here. Well, we'll come back to it. Okay.
So that would Diffie-Hellman as in HMAC.
Yeah. Yes, and I'm not sure the details because Diffie-Hellman is used in a number of different ways, and they're affected to a different degree. Okay, so here are some of the new algorithms, the ones that have been put into a new U.S. government standard. So for asymmetric, we have FIPS 203, which came out 2 years ago. It's called Module Lattice-Based Key Encapsulation Mechanism Standard, MLChem. There's another, so that's used for key encapsulation. You wrap the symmetric key before you transmit it over a link that can be monitored. FIPS 204 is Module Lattice-Based Digital Signature Standard, MLDSA, and digital signatures are also part of all of this. Something I need to mention right here, you may have heard of these under the original name of the submission to the competition, crystals Kyber and crystals dilithium. And one of those two, there were significant changes between the initial submission and what came out in the standard. So if you're going to implement this stuff, you must use FIPS 203 and 204. Don't go back to the original submissions because in one case, there have been significant changes, and you would not be implementing it correctly. And there are smaller changes. Another one that is used actually came out 5 years ago, 800-208, and they are algorithms for signing firmware and software. One implements the Leighton-Macaulay signature, LMS, and the other is the extended Merkle signature scheme. And again, I don't know the details of any of these, but that's what's in that standard. Okay, so oh yeah, Shyam?
Any reason you didn't list SLH DSA?
I'm sorry, say again?
What reason, any reason you didn't list SLH DSA?
I'm sorry, I'm still not hearing you clearly. Any reason?
Any reason you didn't list SLH DSA? That's the other algorithm.
There have been
I
several
don't-
additional algorithms above
Yeah.
and beyond these that have announced that they're going to be standardized, including I think it's on Hammy codes is another one. So
Oh, I'm sorry, John, could you sorry, we need to get you recorded.
In addition to these listed algorithms, there are several additional algorithms that have been standardized or proposed and announced that they will be standardizing. So it's basically become an acronym soup of algorithms. So when someone says post-quantum crypto, it's not one, it's like 6.
Yeah. And the ones I'm emphasizing right here are the ones that are being proposed for national security systems. And I'm coming to that very shortly. So yeah, there is more than this. So the transition. The government has published the Commercial National Security Algorithm CNSA Suite 2.0. And this has most of the algorithms I've already talked about. And these include post-quantum crypto algorithms for use in what are called national security systems. Okay, what if I don't want to sell to the government? Well, a lot of people are just going to want to implement once, so they would like to sell to their commercial customers the same storage systems that they would sell to the government. So that's why everybody needs to pay attention to these and think very carefully about whether you want to do something different than what's in CNSA 2.0. There's some squishiness here. The UK timelines for adoption run fairly close to CNSA 2.0. EU is somewhat different, and that's kind of changed over the last few months, and I don't want to dive into that. It may or may not be relevant to you. So here is what's in CNSA Suite 2.0, and these are not all of the ones. As William mentioned, there are a whole, as you said, alphabet soup of algorithms, but these are the ones that this suite needs. So to begin, as I've said before, RSA, finite field Diffie-Hellman, and elliptic curve cryptography are generally being deprecated. And some of these are older standards, and they have specific uses for which they are okay. 180-4 is the secure hash standard, the old one, not SHA-2, not SHA-3. 384 and 512 are allowed. 197, which is AES, is constrained. The smaller keys are deprecated, so it's only in compliance with CNSA if you use 256-bit keys with AES. FIPS 202 is the SHA-3 standard, and it's permutation-based hash and extendable output functions. This has been around a long time, and this one is approved only for hardware integrity checks. Randy, do you want to ask now or wait till I get through the bottom?
you can get to the bottom.
Okay. 203 is one of the new ones, module lattice-based key encryption mechanism standard. That's fine for any key encryption use. Similarly, 204 for any digital signatures. And finally, 800-208, I mentioned, those are good for signing firmware and software, but they also have a couple of algorithms, HSS and XMSS-MT. For whatever reason, those are not allowed. So LMS and XMSS are the only two out of SP 800-208 that are allowed. Okay, Randy.
So this is what I've been dying to ask is, why 256? I mean, we're talking about for quantum, that's a quality change. How does a bit length change save us?
Okay, essentially what happened with Grover's algorithm is it was able to weaken it by about half. And so by going up to the longer key length, you retain approximately the same level of security. Well, wait for the microphone.
What?
No, I'm sure he can explain it or whatever.
Not me.
Oh, okay. I was just going to clarify that Grover's algorithm applies to symmetric key algorithms?
Yes.
And that reduces the bit strength by about half.
Yes.
So by specifying a minimum of 256, we're getting old 128.
Right. Okay.
But all right,
Randy does not. Okay, yeah, pass the microphone back.
So that doesn't mean that 256 is okay. That means that you need to use double whatever you were using before. Because I know of applications that 256 was okay, and they were okay with that.
Yeah.
They wouldn't be okay with 128-bit. So that's a... I'm not sure how to phrase this appropriately. That's a disservice to say at least 256, because that's not what I'm hearing. What I'm hearing is that we should all be doubling our keys.
Right. The problem is with AES, 256 is the largest key available. It is. And it has to do with the number of cycles of encryption. But they've judged, sorry, are you hearing something different?
But that means
Yeah.
it's not okay.
A lot of this, yeah, it's not okay. Well, NIST thinks it's good enough for now, and honestly, like I said, I'm not a cryptographer. I'm not able to go into details. Sure. So, okay. But for purposes of CNSA 2.0, they've decided that AES, the existing AES, using 256-bit keys is good enough for now. Okay, so where are we in the transition? So we've got a sufficient set of PQC algorithms. Those have been standardized. Now the focus is on transitioning the various protocols to use these PQC algorithms. And Jeff Hillen was talking about this in the previous hour. And along with transitioning the protocols, you transition the libraries that implement those protocols. So what are the issues? Well, for one thing, the PQC keys are large. For example, RSA keys. What's the largest RSA key? Was it 3072 bits or 4096 bits, something like that? Some of the PQC keys for the algorithms I've shown, and I'm not speaking authoritatively, I believe they're in excess of 10,000 bytes. Does that sound right? Yeah, okay, I'm getting nods from the back. So they're really big. And that can turn into problems if your protocol has like a key length field that isn't big enough to represent a number that big. So that's why people are having to go back and work on things like TLS and X509 certificates. Let's see. Right, TLS, there's certificate signing involved and TLS key exchange, et cetera. So how do you interoperate between old devices and new devices during the transition period? Well, there are two schemes. One way is to deploy products that implement the vulnerable algorithms, but that can be upgraded to use the new quantum resistant algorithms. And at some point, you go out and you either upload new firmware or you have a switch that can be thrown that says you will now go to the quantum resistant algorithms and never use the others. The other approach is to use hybrid algorithms that actually use both the classical and the PQC algorithms to provide security. And the hope is that only one of those is going to be broken at a time. So you at least have as good security with one of those. Now, if both are broken badly, then you've got a problem. And I will say that apparently during the during the competition or even afterwards, one of the algorithms that had been approved, one of the PQC algorithms, was found to have problems. And so they had to withdraw that and never issue it as a FIPS standard. As somebody once said, all it takes is one smart person and all of this falls apart. Maybe. Okay, so either deploy products that you can flip from one to the other under command, or deploy products that do the hybrid algorithms. So where do we need this? Hybrid algorithms for TLS 1.3, secure shell, X.509 certificates. NIST has said they are not working on, at least not publicly, on trying to standardize any hybrid algorithms. That work has been going on mostly in IETF and the Internet Research Task Force. This is kind of a laundry list of some of the work that's going on. RFC 9180 is called Hybrid Public Key Encryption. To my knowledge, this is, yes, that was published in 2022. There are post-quantum cryptography recommendations for TLS-based applications. By the way, all these underlying things here are links. So when you download the presentation, you can go chase them down. There's a hybrid key exchange in TLS 1.3, on and on, numerous others. And a lot of them are still in the work. And we have the, okay. Oh, yes, let me back up. Hybrid is the simultaneous use of a classical algorithm and one of the new PQC algorithms. So for example, well, I can't explain the algorithms, but basically you're using keys of each type, and your security should be at least as good as the weaker of those.
For instance, a double wrap.
Yeah, that's one way to do it. Nope, sorry, you had your hand up first. You're next, Sham.
Well, what John just said, you're wrapping the old encryption inside the new one. And an important part of that is that you can't be reducing the security compared to what you had before.
Yep.
Since you're still using the old algorithm, you're just adding the new one. And since
Correct.
these new approaches are so new, we don't have the experience with them yet. They could be completely broken. We may need to replace them at some point soon if they're broken. You can't rely upon them. So again, you're just adding and not removing any security.
Right, thank you. That was a better explanation than I was giving.
Just a comment that hybrid should not be confused with dual signing, and that's my PSA.
I don't believe so.
Yeah.
Okay, so here's a laundry list of protocols. I found out from Dave Peterson at Brocade that Fiber Channel Security Protocol 3 is incorporating PQC algorithms. DMTF, we heard about in the previous section, and then there are a lot of others. DICE, the TCG's device identifier composition algorithm. Secure shell needs to be updated. IPsec needs to be updated. And something I really don't know much about, cryptographic message syntax. So these are just a few of the protocols that are being updated. So when you update, and for example, I don't know the status of, say, OpenSSL, but they implement all, or many, if not all of these. So those are the sorts of software that will be affected by this. Something very important about TLS 1.3. The large PQC keys are being incorporated, including the new certificates, but there's been some confusion. You cannot say, this is TLS 1.3 compliant and assume that it has any PQC protection, because TLS 1.3 has been out for a few years, at least. However, it supports different cipher suites. And if those cipher suites don't use PQC algorithms, then they are not quantum resistant. But if you do, if two endpoints who are talking support the same cipher suite that does support, that uses a PQC algorithm, then you do have the protection. So the main thing is consumers of implementations that say they comply with TLS 1.3, you have to ask more questions and find out exactly what PQC, whether they support PQC algorithms. So it's something I was kind of surprised, but apparently some people have thought TLS 1.3 compliance means it has PQC protection. It does not. Others, and again, Jeff Hillen talked about this in the previous hour, SPDM 1.4, which is the standard number is DSP 2074 out of DMTF. They support MLChem, MLDSA, FIPS 205, which is stateless hash-based digital signature standard, and then 800.227, which is not quite published, if I remember correctly. And those are recommendations for key encapsulation mechanisms. Something you will find are recommendations that come out, and they recommend how to use different algorithms without actually, and the algorithms themselves are defined elsewhere. But if you want to use them, you need to follow the recommendations. I had thought there was a serious target to put hybrid algorithms into SPDM 1.5, but apparently this is not true. Because the availability of published standards for hybrid algorithms is uncertain. They're still in flux. So we don't know when SPDM is going to support quantum-resistant algorithms. Let's see, over in the trusted computing group, I've already mentioned DICE. That is going to change to accommodate larger keys, unless it has already. I don't think it has. Yeah, Bill?
Yeah, and that actually related to the question that I was going to ask. And this is a naive question from somebody who's not immersed in the storage world. But a number of storage devices have the PSID of a 32-character key to unlock a device. Is this going to explode that? Or are we going to be looking at 320-character PSIDs?
I don't know how DICE, John or James, does anyone know what the plans are for DICE and how are things like PSIDs? Yep, hang on.
So details to come.
Okay, the answer is, Bill, we can't answer that right now, the people who are sitting here, but it's an excellent question. Okay, and then there's a DPE, DICE protection environment, that's going to similarly change. That's all out of Trusted Computing Group. Libraries, these will implement them. I'm not sure of the status of updating each of these, what cipher suites they currently support, but there's OpenSSL that everybody's used for years, Boring SSL, which is amusing, LibSodium. Does anyone know what LibSodium is used for? I don't, but I found it in a list of things that will be updated. The Java cryptography architecture, and there are more. So whatever protocols you're using, look for changes in those and ask the questions. So I guess I'm coming down to the end of this talk. So here's a call for action. Systems and devices that use XTS-AES will need to meet the new keyscope limitations. And so there are all sorts of implementation questions. You're given a target by the new version of 1619, but no implementation guidance. Support for these algorithms needs to be developed right now. Because, for example, actually, I'm sorry, I want to back up because I thought I had some more of the timeline in here, but perhaps I took that out. Yes, I did. I'll just say that in the supporting materials at the back of this, there's a lot more information that'll resolve a lot of ambiguities about NIST accepting different implementations and when the requirements go into effect. The bottom line is that the government was expecting or is requiring anything sold into the national security systems to be fully compliant, totally implemented in 10 years, by 2035. And one thing to watch out for is that devices are expected, the last I heard, when you sell to the government, to have a 7-year lifetime. So if you're going to sell anything within the next couple of years and expect it to last that entire time, you better have the PQC support at least enabled, so you can maybe do a firmware update or something like that. Because if if you don't have a very, very clear path that you can show to your test lab of getting to full compliance by the deadline, then they may not buy your device. And part of this is customers and vendors need to come up with plans. You know, at this date, I will get a device that has these capabilities. You will give me an update by this date, and on and on. And it's going to require a lot of deep dive on both sides, by both the customers and the vendors. And they need to talk to each other. Because if you make some assumption, it's not going to, you may well find yourself in trouble with your customers. Okay, so thank you for attending. So we have some time. How much time do we have left? About 10 minutes? 5, okay.
So, by the way,
Yeah.
I tried to download the presentation and it's password protected. Was that intended as an exercise for the students?
Yeah, feed that into your array of, see how many GPUs you need to run for how many days to break that encryption. I bet it's...
on the screen for providing...
I know, and this version of this presentation has not been uploaded. I'm going to mail that off to Brooke shortly.
The key question is, was it AES 256?
And yeah.
So you just told us about U.S. algorithms for encryption.
Right.
Can you talk about China and algorithms related to China?
I cannot. I have not dug into that real deeply. John, do you have?
No, and I'm afraid I know they're there,
Yeah.
but
Yeah, China is developing their own crypto suites. The UK, I believe, is sticking with the algorithms promoted by NIST. EU is a little bit squishier. And sorry, let me. These are all various guidances, and there's a lot of really good information here, especially in those first two. But you have to read it very carefully. It goes into all sorts of corner cases and what are really strong requirements and what are less strong. And so this transition is very complicated. And those top two documents give you the best place to go figure out what you have to do. I'm sorry, I wish there were very clear answers, but they're not. So, yes?
So I want to follow up that question, like, because AES XTS 256 is the only thing we have right now. So if we want to do a little better, is there anything available for block storage and stuff like that?
Not until the new version of FIPS 197 comes out with the 256-bit encryption block and a 256-bit key. So the answer is no, not now. AES with a 256-bit key is the only good thing that I am aware of right now.
What was that EME2 variant that you had on the slide?
I don't remember the details of that. And like I said, that is all for what's called wide block encryption. Oh, yeah, sorry. The question is, what is EME2-AES? That's in the only thing remaining in the new version of 1619-2. I honestly don't remember the details of that. You can pull it down maybe and take a look at it, but unfortunately, the IEEE standards all have to be purchased.
unless you join CISWIG.
Yes, if you join the working group, you get your copy.
I believe it's also AES GCM that's the standard, right, in 256 for CNSA 2.0, not XGS.
Sorry? Somebody else had a comment? An answer?
Anyway,
okay.
that was a comment. So back to the authentication portion. There is standardization now happening around the hybrid modes, like the CHEM X25519, Kyber 768.
Yeah.
Is there any talk around CHEM TLS standardization?
I would have to dig into some of those IETF and IRTF standards. There's one specifically for TLS 1.3, and that's the one that tells you. I don't know right now.
So currently TLS 1.3 only supports the hybrid. CHEM TLS is implicit for authentication for those that aren't aware. But
well, TLS, there is a standard under development that would explain how to use hybrid with TLS 1.3, but it's not published as an RFC right now that I am aware of.
Okay, so I mean, it is used in industry, right?
Yeah.
Not as TLS 1.3, I suppose, but.
Right. So yeah, hybrid's in flux right now.
Yeah.
And we're all trying to catch up.
I don't think hybrids are being used right now.
Well, so hybrid is being deployed by Cloudflare at the moment. They use X25519 Kyber 768 on their authentications. But so I thought it was part of TLS 1.3 standard, but I could be wrong.
The question is the way to use hybrid in TLS 1.3, has that been a ratified spec yet? Is it is it an RFC or is it just an internet draft at this point? And as far as I know, it's still just an internet draft.
Okay, no, that makes sense.
And that's something that Jeff Hill had mentioned in the previous talk. They are waiting on getting PQC hybrid algorithms into SPDM until they actually have published specs.
Okay, that makes sense. I guess my question's more, so for those that aren't aware, and I know I missed the previous session, so tell me if I missed it, but for ChemTLS, so the hybrid mode, there's essentially an extra step that you're doing to bring in the X25519 wrapper into it for the authentication portion. But ChemTLS actually effectively removes that, so it takes one step out of the entire authentication portion. The difference is it's implicit authentication that you get with the or the encapsulation operation itself. Mm-hmm. Is there any notion that TLS would move to that as the support portion, or is it standardizing on a hybrid support portion?
I honestly don't know. I haven't been following that piece of the puzzle that closely.
Okay.
So you probably know more than I do, and now we know what you know.
No,
Sorry.
fair. That's a question to the room too. I'm genuinely just kind of curious. So,
does anyone else have any other information on that? Yeah, Shyam? Oh, okay.
So I don't know if you've covered the X.509 extensions, but I know there's some related to including the PQC stuff.
Let me see if I have an actual reference for the X.509 stuff. Not, let's see. Not directly. I don't know which standard is going to update 509. So, yeah, I just had that mentioned. That's all I had time to dig up. More questions? I guess I'm leaving you probably with more questions than you had when you came in. Sorry, but it's the whole...
But I do suspect that in the storage world, we will probably have to do what PCI SIG just did to invent get key type situations where we can change the key on the fly once we've overused it by writing multiple times into our devices.
Mm-hmm. Oh, okay.
Opening up yet another.
No. Well,
John, okay.
That's a rat hole we could spend a while exploring, but we're out, I think, for pretty much...
Can we rekey this presentation?
Yeah, that's a key point, and we can make puns about that for a while. Okay, anything else before we close? Okay, thanks very much, everybody.